In heavy iron, stability means being bolted down. But in 1966, engineers in Allentown built a transmission where the most critical shaft just floats free. No bearings at the ends, nothing holding it but the math. That gearbox insulted every veteran gear jammer on the road, proved 15 gears were 10 too many, and ran cooler than the physics said it should. They called it the whine of the dog. The industry called it impossible. History calls it Maxitorque. By 1964, Mack Trucks was bleeding out. The company that built its name hauling artillery through the mud of World War I was losing a financial war it didn't fully understand. Between 1959 and 1964, annual earnings collapsed from $15.8 million down to just $3.4 million. The suits had moved the executive offices to Montvale, New Jersey, physically separating themselves from the engineers and machinists who knew how to build a truck. Work stoppages followed, and the workforce had stopped believing in the product. The highway was the other big problem. The interstate system was open and moving freight fast, and Detroit Diesel had the market tuned to a screaming pitch. Their two-stroke 8V71 turned RPMs like a race engine, and drivers loved the sound of it. Caterpillar's 1693 was hauling hard up mountain grades where a Mack would lug down and fall behind. The Thermodyne engine Mack had been building for years was honest iron, but it operated in a very narrow power band. When a loaded Mack truck hit a grade and the RPMs dropped, the engine ran out of breath fast, and the driver had to grab a lower gear or watch his momentum die. On the highway, that wasn't just a quirk, it was a liability. The Chrysler Corporation tried to buy Mack outright in 1964, but the Department of Justice blocked it on antitrust grounds. There was no rescue and no new capital, leaving a company standing alone with aging factories and a product that was losing ground every single day. The board brought in Zenon Hansen to fix the mess. He'd run Diamond T and been an executive at White Motor, which was the same company now circling Mack as a takeover target. Hansen was loud and direct, and he wasn't interested in managing a slow decline. He moved the executive offices back to Allentown and walked the factory floor personally to hand out bulldog lapel pens to the line workers. He made one thing clear. The company was going to build something the industry had never seen, or it wasn't going to be a company much longer. The mandate went to Walter May, the VP of Engineering, and May responded with something radical. The problem he was trying to solve was a mechanical physics problem. Mack's new Maxidyne engine was being developed by Winton Pellizzoni to push peak torque down to 1200 RPM instead of chasing high revving horsepower. This produced so much low-end twisting force that it destroyed every conventional transmission they bolted to it. Gear teeth sheared and shafts bent because standard single countershaft designs simply couldn't handle the load. The industry's answer to that problem had always been bigger steel, thicker shafts, heavier cases, more mass. But May knew where that road ended. A transmission built heavy enough to absorb Maxidyne's low-end torque through brute force would be too long to fit under a standard cab, and too heavy to leave a fleet manager with a legal payload worth hauling. Bigger steel wasn't a solution, it was just a slower way to lose. May needed a way to handle 1,228 Nm of twisting force through a compact, lightweight case without adding the mass that would make it viable in the first place. By every conventional engineering principle of the era, that was a contradiction with no answer. His solution didn't involve more steel at all. It involved a piece of geometry that the industry hadn't seriously considered at this scale, and when the finished transmission came off the bench, it appeared to violate the basic physics of how mechanical force was supposed to work. When the first prototype survived the torture rack without shearing a single tooth, Hansen didn't quietly sign the production order. He walked the factory floor in Allentown and told the machinists it was over for the competition. It wasn't just a gearbox coming off that bench, it was his vindication. Instead of fighting the forces, he balanced them. He surrounded the main shaft with 3 countershafts, spaced exactly 120 degrees apart. Every countershaft carried 1/3 of the load, so the radial forces pushing into the main shaft canceled each other out perfectly from 3 directions at once. The math was clean, 3 equal forces, perfectly opposed, summing to 0. The main shaft had nothing pushing it off center, no deflection, no radial load, nothing trying to bend it out of position. Because of that, they pulled the end bearings off it entirely. The shaft centered itself using nothing but the geometry of the gears surrounding it. It floated, and it held. The floating mainshaft solved the engineering problem, but what nobody anticipated was that it would start a culture war. When Mack rolled out a Class 8 truck with a 5-speed transmission, the veterans on the road took it personally. These were men who had spent entire careers mastering a physical skill, reading engine pitch by ear, timing a double clutch perfectly, threading 2 shift levers through a sequence under load. That skill determined who got hired and who got sent home. A 5-speed said none of that mattered anymore. To a man who had spent 20 years playing the sticks like a piano, the simplicity wasn't a gift. It felt like the machine was telling him he wasn't needed. They called it a neutered dog on the CB, and every time a field trainer told a driver to stay out of the clutch, it was a battle of wills between a man's pride and the math. The math didn't care about pride. But the culture war was really a physics argument, and physics don't negotiate. Here's what actually happens every time a driver in a 13-speed rig hits a steep grade. The engine bogs, and the instinct built over years of running narrow power band engines fires immediately. He grabs the clutch to find a lower gear, but the moment it goes in, the mechanical connection between engine and drive wheels disappears. The turbo spools down, exhaust pressure drops, and when he re-engages in the lower gear, the engine is chasing boost from nearly zero. That thick black smoke from the stacks isn't power, it's the exact moment traction breaks and the truck stops moving. The Maxidyne solved this at the source. As the engine lugged from 2100 toward 1200 RPM, the fuel pump increased delivery and torque actually rose 52%. The driver's only job was throttle down, clutch out. The turbo stayed spooled, exhaust flow never broke, and the truck pulled through without surrendering a foot of momentum. That same heavy pull took a fraction of the time to navigate, putting serious money back on the clock every single cycle. Over a full shift and across a whole fleet, that math compounded fast. Contractors who ran the numbers didn't stay loyal to other brands for long. The Maxitorque also ran cool because the triple countershaft design eliminated the heat problem before it could even start. With friction split 3 ways across the gear faces, no single contact point generated the kind of localized heat that would cook a standard 90-weight gear oil. The aluminum casing pulled heat out of the gear set and radiated it passively into the air, which meant there was no external oil cooler and no hydraulic lines to rupture on a rock. On a construction site or a logging road, having one less failure point is worth more than any spec sheet can measure. Mack knew drivers weren't going to believe any of this without proof, and they also knew proof alone wouldn't be enough to change minds. Muscle memory is harder to reprogram than a fuel pump, so they riveted a metal plate right next to the dashboard, right next to the tachometer where the driver couldn't miss it. It was stamped in honest metal, telling the driver to operate between 1200 and 2100 RPM and not to downshift until the engine hit that lower limit. The plate was a flat-out admission that the engineering was correct and the drivers were the ones doing it wrong. Mack even sent field trainers to climb into the cabs and physically stop drivers from reaching for the shift lever when the engine started to lug. The trainers had one simple instruction, which was to sit on their hands and watch what happened. What happened was the truck pulled through every single time. Once a driver felt the momentum paradox firsthand and watched a machine do more work with less effort than anything they'd run before, the argument was over. Physics won. The 5-speed solved the highway, but the job site had a completely different problem. Solving it turned the Maxitorque into something nobody originally designed it to be, a financial instrument. On a large earth-moving or grading site, the math that governs profitability isn't about horsepower or top speed, it's about cycle time. You have to look at how long it takes one truck to load, haul, dump, and return to the shovel. That single number determines whether a contractor makes money or loses it when it's multiplied across a fleet running 10-hour shifts. Fleet managers and site accountants track that number like a heartbeat. The problem was reverse gear. Standard commercial transmissions treated reverse as an afterthought, so it was usually just one slow cog designed for backing into a dock, rather than covering real ground. A competitor's dump truck reversing down a long grading corridor to reach the loading shovel was limited to 2 or 3 miles per hour. If that corridor was a quarter-mile long, the return trip ate up 7 or 8 minutes of dead time while the shovel sat idle, and the foreman watched the clock. Mack addressed this with the quadruplex, which was the 5x4 configuration of the Maxitorque known as the TRQ 7220. The unified design of that transmission meant the reverse gear interacted with the auxiliary compound section the same way the forward gears did. When you engaged reverse, you still had access to the 4-speed auxiliary box, which meant you could actually build speed going backward. A loaded Mack dump truck could reverse at speeds pushing 15 miles an hour, cutting that corridor time to shreds, and putting real money back on the clock every single cycle. The foreman didn't need a spreadsheet to see what was happening. By midday, the Mack fleet had moved a fifth more dirt than the competition, and the competition's trucks were still backing up to the shovel. The gap didn't show up in a brochure, it showed up in who got called back for the next contract. The driving experience of that quadruplex was something else entirely. The 5x4 ran twin sticks, two levers that controlled the main box and the auxiliary section independently. Getting a loaded 10-wheeler moving from a dead stop meant working both sticks through a sequenced pattern, dropping the main lever from first into second while simultaneously throwing the auxiliary back to low in the same instant. Both hands off the wheel. Timing off by a half second and the gears rejected the shift while momentum bled away. Drivers called it a ballet, and they weren't wrong. The engine feeding all of this was the NT676, better known as the Maxidyne 285. That horsepower rating looked modest against the competition, but the torque at 1200 RPM is what actually moved the dirt. Pushing output higher meant forcing more oxygen into the cylinders, and turbocharging does that, but compressing air heats it up and kills its density. Mack's answer was borrowed from aerospace, the tip turbine intercooler, which bled high-pressure air off the main turbo to spin a dedicated fan with zero crankshaft drag, scrubbing heat out of the intake charge before it hit the cylinders. The distinctive high-pitched whistle of that tip turbine spooling under load became the sonic signature of the 1970s Mack, working hard. Then, October of 1973 hit. OPEC cut the oil supply, and diesel prices quadrupled, which meant every fleet manager in America suddenly cared deeply about fuel consumed per mile. The high-revving engines that had dominated the market became liabilities overnight. The Maxidyne's low RPM lugging profile was the exact characteristic veteran drivers had mocked, but now it was the only thing standing between a fleet surviving the year or liquidating its equipment. The weird experiment became the gold standard, and it happened fast. The fuel crisis proved Mack was right about the American highway, but the real test for that transmission was happening in a place where the highway didn't even exist. During the 1970s, Australia was a logistical nightmare. The interior was finally opening up as mining operations, massive cattle stations, and drilling sites popped up across the Northern Territory and Western Australia. Yet, the rail lines couldn't reach any of it. The only solution was the road train, which meant a single truck pulling 2 or 3 trailers and moving over 100 tons of payload across hundreds of miles of corrugated dirt track. Temperatures on the Stewart Highway regularly pushed 110 degrees, and the red bull dust coming off the road was so fine it found its way into every seal and bearing. Standard transmissions simply didn't survive the outback. They worked fine on pavement with moderate loads, but dragging 100 tons across sun-baked dirt at low speeds for hours created a thermal nightmare. That kind of sustained torque load generated constant friction between the gear faces, and in that 120-degree heat, the gear oil would thin out until it stopped protecting the metal. Transmissions that used external oil coolers to fight the heat had a fatal flaw because the vibrations from the washboard roads would rattle the cooler lines loose or send rocks through the cores. A ruptured line meant the gearbox would pump itself dry in minutes, and in the middle of the outback, a dead transmission wasn't just a breakdown, it was a threat to your life. The Maxitorque didn't need those external coolers because the triple countershaft design spread the friction load across 3 points before the heat could spike. Whatever heat did build up was quickly pulled away by the aluminum case. Mack's R-Series trucks and the later Superliners became the backbone of the road train industry because they kept moving while the competition left their oil in the dirt. The Australian truckies didn't buy the Bulldog because they liked the logo. They bought it because the alternative was being stranded 200 miles from the nearest phone. On the other side of the world, the Maxitorque was proving itself in the steep forests of New Zealand. Logging crews in the Kaingaroa forest hauled 154 tons on private dirt roads that were never built to highway standard. Getting a loaded logger moving from a dead stop on a 15% grade required a gear reduction that standard transmissions didn't have. Slip the clutch on those hills, and you'd incinerate the friction plates before the truck moved an inch. The T310M compound gear set offered a forward ratio as low as 17.35 to 1, enough leverage to break inertia on a massive load without snapping the driveline. PTO mounts on both sides of the case meant the same gearbox that moved the truck also powered the hydraulic winches pulling the timber out of the ravines. This era gave birth to the Gold Bulldog. Mack had used the ornament for years, but by the late 1970s it became a way to tell everyone exactly what was under the hood. A gold-plated Bulldog meant the truck was pure Mack, from the engine to the Maxitorque and down to the drive axles. Silver meant there were third-party parts somewhere in the mix. In the Outback, that wasn't a marketing distinction. When you're 300 miles from the nearest town and the temperature is pushing 120 degrees, the hood ornament tells you whether the machine under it was built to survive or just rated for highway use. The gold bulldog wasn't a gimmick, it was a mechanical guarantee, backed up by every mile those transmissions had already run. The problem with winning an argument is that eventually your competition figures out the right answer too. By 1976, Cummins had seen enough of Mack's success. They knew exactly how Walter May had designed the Maxidyne's fuel curve, so they copied their homework. The Cummins NTC 290 Big Cam used a redesigned camshaft with steeper lobe profiles to push the injectors harder and create a violent combustion event at low engine speeds. It put out 1260 Nm of torque at 1300 RPM and could lug a load up a grade just like a Maxidyne. Because it bolted into a Kenworth, a Peterbilt, or a Freightliner, fleet managers finally had a way to get Mack performance without being locked into Mack's parts system. The Motor Carrier Act of 1980 pushed the door open even further. When the government stopped setting freight rates, the era of protected margins ended overnight, and rates plummeted as new companies flooded the market. The guys in the front office started looking at spreadsheets instead of spec sheets. Fleet buyers couldn't justify the premium price of a Mack, when a standard Cummins and Eaton combo could be fixed at any truck stop by any mechanic with a basic toolkit. To keep up with the new demands for fuel economy, Mack had to kill off one of Maxidyne's best features. The tip turbine was a clever, compact design, but it had a thermal limit, and could only drop intake air temperatures down to about 220 degrees. That worked for the 1970s, but new emissions laws and the push for better mileage required a much colder, denser air charge. Mack moved to a chassis-mounted charge air cooler at the front of the truck, which used the wind at highway speeds to pull temperatures down to 110 degrees. The physics worked, and the engineers saw a massive jump in fuel economy. However, the long plumbing needed to reach that front cooler required bigger turbos just to push the air through all those extra pipes. This made the turbo response sluggish, and the famous high-pitched whistle of the tip turbine finally went silent. Mack rebranded the engine line as the Econodyne, and while the name was honest about the fuel savings, the soul of the machine had changed. The transmission was starting to show its age too. The original 5-speed Maxitorque was a masterpiece of simple gear geometry, but as the market demanded more gears, Mack bolted on compound auxiliary sections to create 12, 13, and 18-speed versions. Shifting those rear sections required pneumatic air shaft valves, and that's where the trouble started. The system worked fine in the summer. During a Minnesota winter at 20 below, it became a liability that no amount of reputation could paper over. Picture this. It's 2 in the morning at a truck stop outside Fargo. The temperature is 22 below zero. A driver hauling 78,000 pounds flips his range selector at the bottom of an on-ramp and gets nothing back but a sputtering hiss. High-pressure air bleeding uselessly past O-rings that the cold has shrunk and seized solid. The shift fork won't move. The truck is stuck between ranges, effectively in neutral, blocking the ramp in a full blizzard. So, he climbs out of the cab, pulls a chemical road flare out of the door pocket, and crawls underneath. He's lying on frozen asphalt, inches from a hot exhaust stack, with 40 tons of loaded iron above him and an open flame in his hand. He holds that flare against the aluminum transmission case and waits for enough heat to transfer through the housing and melt the ice inside the shift cylinder. If he holds it too long, he risks igniting the gear oil residue on the case. If he doesn't hold it long enough, the valve stays frozen and he's not going anywhere. That was the field reality of the Bulletproof Mack in the 1980s. Road flares, propane torches, rags soaked in diesel and lit on fire. Drivers injecting alcohol antifreeze directly into the air lines and praying it reached the valve before something worse happened. The legendary triple countershaft design was still intact inside that case, but nobody was talking about gear geometry at 2 in the morning in a North Dakota blizzard. Despite the frozen valves and the corporate shifts, the Maxitorque held its ground for one specific reason: the way it was all put together. The T300 series was designed in 2 separate pieces, so a mechanic could actually fix the thing without dropping the entire heavy unit out of the truck. You unbolt the rear bearing cover, pull the countershaft covers, and take out the synchronizer pins. Once those sliding clutches are out, the whole mainshaft assembly slides right through the back of the case, while the bell housing stays bolted to the engine. The truck stays on its wheels, and the work gets done right there on the shop floor. A man with a standard set of hand tools and a clean workbench could rebuild one of those gearboxes from top to bottom without a dealer or a diagnostic laptop in sight. It was just cast aluminum, hardened steel, and the kind of mechanical knowledge passed down from an old-timer to the guy watching over his shoulder. That rear loading design is the real reason these transmissions hit 1,000,000 miles. The parts weren't necessarily indestructible, but the design allowed a mechanic to catch a failing part early and swap it out before the whole box turned into a pile of scrap metal. Mack kept it simple, with a magnetic drain plug that pulled metal shavings out of the oil and a splash lubrication system that didn't need a pump. The lower countershaft just dipped into the oil reservoir and threw lubricant up onto the main shaft gears every time it rotated. There was no hidden complexity to fail you when you were miles from home. Mack understood that complexity is where the gremlins hide, so they simply built the complexity out of the machine. The E9 V8 was the final time that philosophy was shouted at full volume. A 16.4-liter four-cycle diesel putting out 400 to 500 horsepower in a standard superliner, and in Australia the EA9 variant pushed past 600 horsepower and 2780 Nm of torque, numbers that made the Caterpillar C16 look like a small block. Paired with a Maxitorque, it was the ultimate expression of what Walter May had been chasing since 1964. Massive torque at low RPM, moving through a gearbox that spread the stress across 3 shafts and stayed cool while doing it. When fleets moved away from the big V8s, the tractor-pulling guys stepped in to find out what the block could actually handle. The iron was over-engineered far beyond any commercial need, which made it perfect for the kind of cylinder pressures that would have shattered a normal engine. These guys were running quad-turbo setups and injecting water just to manage the heat, and the E9 took it. The end of that era didn't arrive with a bang, it arrived with a line of code. Renault had been buying into Mack since 1979 and took full control in 1990. Volvo bought the whole Renault heavy truck corporation, cleared the antitrust hurdles by selling off its North American cab-over business, and on January 2, 2001, the Bulldog belonged to Sweden. The machinists who had been in that Allentown factory floor since Hansen handed out Bulldog pins in the 1960s watched their product become a badge on someone else's platform. The men who knew how to feel a main shaft for runout by hand were being replaced by technicians who read a screen. The grease-stained engineering blueprints from Allentown were now part of a global corporate platform built around interchangeability. The transmission went from being something a mechanic could feel and rebuild to being a node on a digital network. That was the moment the truck stopped being a machine you understood through your hands and became a computer you managed through a screen. The M drive that replaced the Maxitorque is fundamentally a Volvo iShift with a Mack badge and custom software. It reads road grade, calculates load weight in real time, and hits the perfect shift point using 9 variables at once. It shifts in hundredths of a second, faster and more consistent than any human. But when the control housing fails, you don't turn wrenches on it, you order a remanufactured unit and swap it out. The mechanic who used to pull a Maxitorque main shaft in a shed with a dirt floor has no way to fix an M drive. That knowledge has no place in a system that runs on code. The 2026 Mack LR Electric puts out over 5,400 Nm of torque at 0 RPM. The second current flows, every bit of that power is available without a single gear shift. Walter May spent his entire career trying to get that kind of performance out of mechanical engineering. The electric motor does it instantly, and in doing so it makes the entire physical world he built unnecessary. But out in the custom fabrication shops, there is a rebellion against that digital future. Walk into one today and you'll see guys spending $150,000 to drop mechanical E7 engines and T300 Maxitorques into brand new 2026 frames. They aren't doing it out of nostalgia. They're doing it because that iron doesn't need a dealership's permission to run. It doesn't derate itself when a sensor reads wrong. A wrench still works when you don't have a cell signal, and out in the dirt, that's the only guarantee that matters. The shift towers are mostly gone now, replaced by plastic buttons. But out in the pits, you can still hear the old-timers listening for that straight-cut gear whine diagnosing the truck by ear before a computer ever throws a fault code. The suits in the boardroom can buy the brand name, but they can't build the soul. At the heart of it all is the exact same piece of geometry Walter May drew up in 1966, a main shaft with no end bearings, held in place by nothing but the math. It floated then, it's still floating now.